Good afternoon, everyone. I think we got about 2 hours to go through this. I do not believe we're going to need the full 2 hours. So just a kind reminder, as I start going through this, if anybody has any questions, please unmute your microphone and just jump in and ask the question. This is for you guys, not for me. Again, the purpose of this class was done put together a few years ago to, at the end of the class, kind of help people have a better understanding of electrical circuits and a better understanding of how to read an electrical schematic and use it to their advantage for troubleshooting. To date, we've covered some basics of electrical. I think the last session was parallel and series circuits. It wasn't meant to scare you away or make you feel like you're forced to do a bunch of math, but again, the exercises were designed to show students simple schematics and then let them kind of dissect them. And so it was more for using their multi-purpose digital volt-ohm meters for training purposes, as well as trying to do a direct correlation between how to look at a simple schematic and build that schematic on a circuit board, or in their case, it was a breadboard. So we did our best trying to do it online, but this is actually my favorite section of the whole class right here. So with this, we'll just get started. So we're going to cover relays and semiconductors. Somebody asked me one time, why did you group these two things together? And I really don't have a good answer. I guess it just kind of fit together, or maybe from time restraints it made sense. But the key about the relays is something that's real dear to me. For years and years early on in this industry, I was primarily a mechanical person. So if you had a vibration problem or a major compressor crash, wreck, et cetera, I was the guy, and I didn't do much with industrial electronics, to be honest. And if somebody can mute their microphone, I sure would appreciate that. But one of the things that was kind of the turning point for me to help understand how to read schematics was learning and understanding the functions of these relays and understanding the pinouts of these relays. So I'm going to do my best to kind of use the next few minutes to describe that. So a relay, what is a relay and why do we use it? Well, for lack of better words, it's an electrically controlled switch. That's all it is. No different than walking to the door by the room that you're sitting in right now. At this moment, there's usually at least one switch on the wall where you can flip a switch and turn it on, but you're mechanically or manually controlling that switch, and this one is controlled electrically. We use voltage with very low current availability to energize the coil that creates a magnetic field inside this relay. When that does, or when the coil is energized, the magnetic field creates and it causes a switch to move contacts inside. So if we think about a single switch sitting on the wall beside your door of your house, in most cases, that is what we call a single pole, single throw switch. It only has one set of contacts in it, and it only can be thrown in one direction or one motion of movement. What we describe the most common relay, which is the picture of what I have here, is just about our most common relay. It's a 6 amp double pole double throw. So what that means is it has two poles in it, or two independent isolated switches from each other. And each one of those can be thrown in two directions. So in direction 1, it does a function. In direction 2, it does a function. So the standard classification is double pole, double throw. So again, two poles or two switches, if you will, inside of this device. The poles or switches are isolated from each other. So you can turn on high voltage with one switch, or a ground with one switch, and even a positive voltage source with the other switch, because they're 100% isolated. Any questions on this so far? Okay. So just about all these relays have a little bit of a schematic on the side of them. And these have become, over the last several years, standard numbering for all relays. So it doesn't matter what brand relay you buy, just about any relay nowadays off the shelf, you're going to see this nomenclature. And they mean something. And I'm going to do my best to describe to you. And I'm going to try not to read all this verbiage in here, but I'm just going to try to describe to you how I interpret this. So the first thing is the coil, and it's indicated by this symbol right here. Sometimes if you're looking at one of our schematics, we'll have a different symbol for that coil, and we'll cover that in our next class when we get into the schematics. But there's generally, in these modern day relays, always an internal diode, and for sure what we call a light emitting diode, that serves as a great indicator that when the relay coil is energized, it lights up. And I really appreciate that because it's a great diagnostic tool when you're in a hurry, and it saves a lot of time. But because of those diodes, they are polarity sensitive. So A1 is the side of the coil that's always going to receive positive voltage to turn on, and A2 is the negative side. So we can turn on and off this relay by two means. We can give it a ground all the time on the A2 side, and we can control the sourcing voltage or a positive voltage signal, whether it's on or off, to energize this coil. Likewise, we can give it a positive voltage to A1 all the time, and we can control when we turn on and off the ground of that coil. So either way is perfectly fine and perfectly acceptable. We're in all of our panel designs, we do it both ways, but if we're using a digital output, in most cases we turn on and off a relay with a ground signal. So again, we have two switches. This is our first pole, and this is our second pole. Each set of switches has a normally closed contact and a normally opened contact, and that's what we would call shelf state. If we energize this coil, the switches are going to both change state, and they'll move from normally closed to normally open. So the nomenclature that I like to tell people here, and this comes in handy when you're trying to rush through and read a schematic so you understand the logic. Well, what state does that relay have to be in for this to happen, for this device to turn on further down the chain in my schematic of my panel? Is you'll notice we have a 21, 24, and 22. We have an 11, a 14, and a 12. So what I tell students that attend my classes is think of this as switch 1 because it begins with 1. Think of this as switch 2 because it begins with 2. If it ends in 1, it's the common terminal. Trace it out. There's our common terminal. It's always going to be connected to one or the other. If it ends in a 4, it's our normally opened terminal, meaning it has to be energized to get contact back to our common. And if it ends in 2, it's our normally closed, meaning if it's not energized, it's going to be contacting our common terminal. Any questions on this part? A lot of students find out when they kind of start understanding that nomenclature, and I encourage people to try to memorize this. When they start really looking at schematics, it helps them to actually fly through the schematics because now they have this kind of imprinted in their head. So we're going to cover a few reasons of why we use relays. Isolation is one of the most common reasons. So if I have a customer that says, well, hey, we have a remote ESD circuit for our station, and maybe they have a square mile of location site, and around that area they might have a series of multiple ESD switches where they could ESD everything, and they always want to tie in an ESD circuit back into one of our control panels. Well, we have no way of knowing what they actually have on that wire that's coming in from their switches. So a lot of times what they'll do is they'll charge their circuit and they'll use 24 volts or a ground signal on and off through their ESD switch to energize a relay. Then we use the dry contacts. If I go back, they'll use the dry contacts to enunciate a kill signal back to an enunciator in one of our panels. That gives good isolation. Never fails. As soon as they say, oh, we have an ESD pair of wires that we want to use, it's dry contacts, they're normally closed, we want to just direct connect to your enunciator. As soon as they do, it never fails. They've got some kind of intrinsically unsafe voltage, or they have some kind of I call it a transient voltage because they say there's no voltage on it, but in fact there is, and they try to wire it directly into a discrete channel on an enunciator product, be it a D3000, a 4000, or even an old school DD enunciator, and the next thing you know, all of our channels kind of start doing I'll just go on and say it, a wig out, because those channels were not designed to receive outside voltage. They produce their own voltage. So isolation is a good reason. Amp rating is another good reason. I might have a contact switch that's capable of switching on and off 1 amp, but I need to be able to provide power in a switched manner to another device that's rated up to 6 amps or even 10 amps or anywhere in between. And then the last reason is logic. So in a lot of cases, we'll do control strategies in some of the panels with what we call relay logic. And any of you that are familiar in reading schematics will understand what I'm talking about. But I can turn on a signal momentarily to a double pole, double throw relay and wire that relay up in a series to where it becomes what we call self-latching, and it will stay energized no matter what that initial switch that triggered it does, and then it has to have another switch or device to interrupt the power to get it to become unlatched. So that's a very common circuit or purpose that we use these relays in our panels for. Another thing is if I have one control device, let's say I'm using a digital output from a D3000, which is a ground, I can use that to energize a relay. But if I'm using it to energize a double pole, double throw relay, then I can do 2 separate functions with that relay. Because it's double pole, I can use one pole to turn on and off a positive signal to a device, and at the same time, I can use a second pole to turn on and off a ground to a device, maybe for an ESD circuit or something. So I can control 2 devices with 2 different types of voltages on them with one output control by using a double pole, double throw relay. And there's also other relays on the market. There's even, I think one of the most common relays we used to use was, some people kind of called it a slang name. They referred to it as an ice cube relay. It was gray. It was about the size of a standard ice cube. It actually had 4 poles in it. So it was a 4-pole double throw relay. And used a separate little magnetic or separate little base to plug into. So we do have a single pole double throw relay that we use commonly now in a lot of our panels. This was something that we sought with this one particular manufacturer to give us. We needed the capabilities to have a good quality 10 amp relay. So if we look at this first relay on the first page that I showed you, that's just the classic relay that we've had for years. It is, some people call this a Christmas tree. I don't see it myself, but it is a green base. It has the orange cartridge in it. It's set up for double pole, double throw. There's a schematic for it, the double pole, double throw. But we used to use a 10 amp relay that was very large, gray, steel casing, class 1 Div 2 approved, but we had a lot of mechanical problems with it. and we sought out to try to find a better quality 10 amp relay. And so this manufacturer was kind enough to produce one for us. So I show this next picture as a caution to you. If we look at the relay on the right-hand side, the cartridge, you can see right in this area, it has an icon. It's representing 2 poles, and each one's a double throw. And this is what we rate this at 6 amp continuous. So it's a 6 amp continuous double pole double throw. Now it may say 10 or 12 amps on it for max, but that's an inrush current, not a continuous. It is 6 amp continuous. The second relay that we now have introduced at first glance looks the same, but if you look right here on the top of it, it has 1 pole double throw. So it's a single pole double throw. It is rated at 10 amps continuous, I think up to 16 amps for an inrush. We've put this thing through some extreme testing and proved that this is an excellent quality relay, even though it's much smaller than it's the one that was replaced by this. It is much more robust, much more reliable. I even have people pulling out now in older panels the old steel cased relay and replacing them with these. Now the only downfall of this is it's a single pole double throw. The dangers of this is be cautious if you have them in your panel. I generally will put a sticker over the tops of these single pole double throws that just say 10 amp to indicate to me when I'm working on a panel, don't try to put this relay in a spot where this relay goes, because they will fit, they will interchange. The pinouts on the bottom sides of them look identical. So the only identifying marks to identify that these are different are these marks that I'm showing on the top. Okay, so that statement's pretty much covering what I was just saying about not trying to interchange them. They will not interchange. If you do interchange, you can do some drastic, I'm not going to say damage per se, but you can make you have a bad day as far as trying to troubleshoot out a problem inside of a panel. So if anybody wants to capture this real quick, here are the OEM part numbers for these 2 cartridges. If you have a flex panel that uses a relay board that was designed in 2017 and put out by the end of 2017, one of those relay boards, we call it a flex panel PCB for the DE3000 flex panel, generally use 6 of the 6 amp double pole double throw relays, part number 2980461, and 1 10 amp single pole double throw relay, part number 2909519. So we're going to skip over the exercise. I don't think that's going to work out too good over the internet here, and we'll just go to the next section. Before we start this next section, does anybody have any questions about relays, horror stories, et cetera, that they'd like to share or ask? Okay. So we're going to move on into diodes. The diode will be classified as a semiconductor. A diode will allow current to flow in one direction, but not the other. So think of it as a check valve. I kind of wrote that out pretty good, I think. It does exactly what a check valve does. It'll let voltage flow in one direction, but not the other. Now, if I've got one particular person listening, he'd say, no, voltage doesn't flow, it's amperage. Okay, technically he's right. Common diode uses rectification, AC current to DC current. So if anybody's ever built an alternator, rebuilt an old alternator, or troubleshot an alternator, and the people that tested your alternator said, oh, your bridge rectifier's out. That's exactly right. A bridge rectifier can take AC current, uses a series of 3 diodes. It takes AC current and converts it into DC current. think the common term was in the 80s for me. I think they called it a diode trio. That was in, say, like a General Motors standard design alternator. Circuit control. Direct current in a specific direction between two circuits. Yep. Clamping protection. Keep voltage spikes from damaging sensitive solid-state circuits. Maintain circuit voltage within a specific range. I added this term in there, self-inductance. So let me take a minute to explain what self-inductance is the best I can do. So if I energize a magnetic field, such as a magnet inside of a standard mechanical relay, there's huge coil of wires in there. Now, maybe it's small, maybe it is real big, but on a standard relay, it's very small. If you unwound it, you're going to find out that you have quite a lot of linear footage of wire that make up that coil. So when you de-energize a magnetic field, a coil of wire such as that, it can go through a process when the magnetic field collapse, when the electrical supply collapses and is turned off, where it has a charge of self-inductance, and so we'll see a little bit of outrush of voltage. And that can damage other sensitive electronics in the circuit. So that's why you'll see whenever we're in a design of one of our panels, whenever we're charging any type of an electrical magnetic coil, such as a solenoid valve out on a compressor package, a relay coil, we will always put in what we call a flyback diode. And you'll see this later. If not today, you'll see it in the next class when we get into the schematics. These modern day relays that I've been talking about with the green bases, the orange, they have a clamping protection or flyback diode built into the relay housing, so we don't have to add it in. Some of the older relays did not have that, and so you would see us in our panel design where we would put our own diode in the design of the panel with the schematic. Likewise, if we're charging a solenoid, it's also an electric field that we're charging, say for like a Versa valve to control pneumatic pressure to open and close a pneumatic valve of some sorts out on the skid for multitudes of reasons. We'll always put a flyback diode in the panel, and that also becomes a place for the customer to tie their wires to go out to. So that's one of the most common purposes of where we'll see a standard diode in an electronic panel. So here's the symbol. It's a silicon diode. You have an anode side and a cathode side of the diode. So notice the triangle almost looks like an arrow. And that almost looks like a stopper or check valve. So the current can flow from the anode side of the diode to the cathode side. So positive can flow this direction to the negative side. But if we put positive on this side, it cannot flow to a negative in this direction. So it's only in one direction. Figure 4.3 illustrates the most common used diode symbol, and that is the most common used. I believe we use that symbol today in every one of our drawings. Here we have an actual diode with a symbol laid out on the ground next to it. The band on the end of the diode indicates the direction of current flow. So if I'm putting this in to try to keep positive voltage from this side to reach this side, I just put it in backwards. But I can put positive voltage here, and it'll keep it from going to this side of the diode. Any questions on this part? Okay. So a diode function test, every meter has a little diode symbol on it. Kind of looks like that. And you can test a diode. Now, the diode has to be isolated from anything else in the circuit. and standing alone by itself in order to test. So if you have one in the panel, don't try to do a diode test in the panel with wires hooked up to it. Disconnect the wires, pull the diode out, then you can do your function test on the diode. Connect the red test lead to the volt ohm meter input connector and the black lead to the common input. Set the function range to the diode position. If the diode being tested is connected to a circuit, turn off the power. All right, that's a disclaimer. Remove a diode from the circuit because you could have other things in the circuit that affect this test too. Connect the test leads to the diode. Read the forward voltage drop on the display. If the display reads OL, reverse the test leads. With the leads properly connected, the forward voltage drop will be displayed. Note, normal voltage drop for a silicon junction at room temperature would be about 600 millivolts. For a germanium junction, about 300 millivolts. So there's two different key functions or two different key materials that they make, the manufacturers make diodes out of, silicon and germanium. I think the most common one that we run into is silicon. If OL is displayed with the test leads in both directions, the diode is open, meaning it has an open circuit. So OL stands for out of limits. If for those of you who remember tuning into the very first class of this electrical series, if a low reading is less than 1 volt in both directions, the diode is shorted. Several times for years, I used to believe that usually when a diode failed, it went open. I'm finding out more and more the older I get that I've actually seen diodes fail more and more, and the opposite of open, they short closed. So the check valve flapper quits working, and now I have flow to, current flow in both directions. That is a bad deal because it can definitely do some damage inside of a panel. If the diode is in a circuit and is shunted by resistance less than 500 ohms, the diode must be removed from the circuit to test. Okay, so we may or may not know the answer to this statement, which is why I changed my statement up here. I recommend, if you're testing a diode, pull it out of the circuit. So just a little quick fun-filled fact. Silicon and germanium diodes are two chemical elements called, we'll just skip over that one. Both silicon and germanium can be combined with other elements to create solid-state electronic devices such as diodes, transistors, photoelectronic cells. Primary differences between silicon and germanium diodes is the voltage needed for the diode to turn on or become a forward bias. Silicon diodes require about 0.7 volts to become forward bias, where germanium diodes about 0.3 volts. And that's pretty much standard. Like I said, most diodes that I come in contact with in our industry are all silicon based. Okay, so here's where you can do a test. I do strongly recommend, if you've never worked with a diode, get on Amazon Prime. I don't think Radio Shacks are in existence anymore, or some little industrial electronic shops, and for fun, go get you one and play with it and know how to use your voltmeter to test it. Any questions on this diode part? Okay. One fun-filled thing, if you have 2 meters available to you, use 1 meter as a diode function test and use another meter just to measure the voltage, DC voltage of your meter that's set up in diode voltage test. You'll see that the digital volt ohm meter actually produces its own voltage for testing these diodes, and that's how it works. Clamping protection. So mini coils are electronic magnets. We've talked about that already. When these magnetic fields collapse, power's turned off, there's a risk of voltage surge. That's where we call it self-inductance. Diodes are used to allow voltage spikes that may place excessive voltage on the negative side of the coil to be rerouted back to the positive side of the coil. This allows for a slower discharge of the magnetic field. This type of protection is sometimes referred to a flyback diode. Oh, I guess I got ahead of myself earlier. Figure 4-5 illustrates a symbol for a Zener diode. So now we're going to talk about a Zener diode. Zener diodes are one of the coolest things in the world. I carry a package of them are actually several packages of them with me at all times. I think I have a few in my computer bag, and I think I have a few under the back seat of my truck, and maybe a few in the console. If you don't have any Zener diodes, I recommend that you carry them, especially if you're dealing a lot with 4 to 20 milliamp current loops. So let's talk about what the Zener diode is. It's a specially designed type of diode, so it's still a check valve. What you're seeing on this page, that's the symbol for a Zener diode that can conduct current in the reverse direction. So it works as a check valve. Current's going to flow still from this anode side to the cathode side as standard. The Zener is designed so that it will not conduct current in the reverse direction below a certain predetermined value of reverse bias voltage. So as an example, a 6-volt Zener diode may not conduct current, jump down to the next page, in the reverse direction until the reverse bias voltage is greater than 6 volts. This type of diode is used to control circuits. In our industry, it's very common when working with 4 to 20 milliamp signals for variable frequency drives and even on Waukesha engines. So I'm going to kind of deviate a little bit from this slideshow and jump into another one, but just let me explain this. So remember, this is our check valve side. So our current as standard can flow from this side of the diode to this side. But if the voltage if it's rated at 6 volts, if the voltage is equal to or greater than 6 volts, all of a sudden the check valve opens up and it'll let current flow either direction. Pretty cool, right? So you would not want to use a Zener diode in a place where you would use a standard silicon diode. So that's one thing. Like if you got a diode in the panel for clamping protection, like a Flyback Diode on a 24-volt system, and it goes bad, and you go digging through your truck and you find a Zener diode, and most Zener diodes kind of look like this color. Most silicon diodes, I'll go back a page or two, actually do look like that. So you would never want to replace a diode that looks like this with a diode that looks like this, because you could be in for hurt. Because if you put this, if it's rated at 6 volts, if you put this on a 24-volt circuit, you just shorted the circuit. So I'm going to jump over to another document, courtesy of Dresser Industries. This is something that they put out several years ago. And what they have is they're showing a typical PLC or a control panel that's generating a 4 to 20 milliamp current loop. And then they're showing their ESM system. And this is true on a lot of devices. I just had a device that I've never had to do this on earlier in the week where they were having a problem. I told them to put a Zener diode in, and it solved their problem. The symptom is I have a variable frequency drive, or in this case, an ESM system, and I'm trying to send it a 4 to 20 signal, but it's not responding. Well, one of the quick tests that I can do while it's wired up is I can momentarily put a jumper wire between the positive and the negative side of my current loop that's feeding into this device. If it starts working all of a sudden after I do that, then I know chances are I probably have an application where I need a Zener diode. So I'm going to do my best to kind of interpret this on the fly with you guys and help you understand what's going on here. But again, the positive voltage is coming in on this positive side of the 4 to 20 milliamp circuit, and it's hitting this Zener diode. It can't get to the other side. It's isolated. But what happens is, as this voltage comes up, if this voltage is greater than 6 volts, if this Zener diode is rated at 6 volts, all of a sudden, it'll let that voltage discharge. So what happens on a lot of cases is some systems go into what they call a self-protect mode. So a good example is if I have this circuit opened for some reason, maybe I have another device sending a speed signal into this manually. And then this device that we see in the schematic is trying to send a speed signal to it at the same time, but it's isolated by a relay for auto speed control. Because the circuits is opened, this device is trying to make this current flow. It can't. So what it does is it starts raising the voltage up. Now when you switch the system and take out the manual speed signal and you close the contacts on a relay that we're imagining sitting in here, and this device connects, now it has more than, it has quite a bit of voltage, up to 24 volts. So this device that's sensing the current loop senses that high voltage, and it goes into what we call a self-protect mode. A lot of electronics in our industry do this. So when that happens, the Zener diode, because it's rated at a 6 volts, discharges momentarily, lets the voltage jump from this side to the negative side, and it brings that voltage back down to a nominal level. And then it allows this device to get out of that self-protect mode. I have seen numerous products. Most common one is variable frequency drives that is just without any hesitation. A lot of times we ship Zener diodes in the panel. So to help prevent problems as described, Waukesha recommends that a 6.2 volt 1 watt Zener diode be placed across all 4 to 20 milliamp inputs, not voltage inputs, to the ECU. This diode may be placed at the signal source, PLC, output card, etc., or at an intermediate junction box commonly used where the customer interface harness terminates. The Zener diode directs excessive high voltage to ground. This safety measure keeps the voltage level in check, avoiding the ECU from disabling its internal input channel for the 4 to 20 milliamp signal. See, that actually said pretty much what I was just describing. It keeps it from disabling itself. And so why was it disabling itself? It's because it was going into a over voltage detected self-defense mode. Any questions about Zener diodes so far and how they are commonly used in our some of our panels and applications in our industry? Okay. So the next one, we get into a light emitting diode. These are my favorite. This is where our classes, when we're doing a hands-on class, has a lot of fun with it. They start getting diodes and they start making them light up, and they have a lot of fun with them. Figure 4.7 shows a symbol for a light emitting diode, LED. The LED will only allow current to flow in one direction, just like a regular diode, but it requires a little bit more voltage to activate the forward bias, approximately 1.5 to 2.2 volts. Now, there's all kinds of different specs of these, but these are the most common. So if you get your hands on a light emitting diode, again, kind of a Radio Shack model, or maybe you take the time to go out and get like a little electronic testing kit. I've got a drawer full of them right next to where I'm sitting. If you hook your meter to it in a diode check and you get the polarity right in the right direction, you'll actually make the diode light up with your meter. A lot of fun. They come in a lot of different colors. They're used for a lot of different things. And as most of us are finding out, you know, because we're going from incandescent light bulbs in our house, we skipped finally and got away from the little fluorescent hazardous light bulbs to now we're running LEDs, and most people are replacing their bulbs in their houses with LEDs. They work a little different, have their own power supply in them, et cetera, but that's what they are, LEDs. So here's some common types or just common LEDs that you might get if you get like a little home LED or electronics test kit. They can be used as standard diodes, but have the illuminated indicator. All relays that we discussed earlier have a third diode in it as an LED. Its main purpose is to serve as a power on indicator. So that is true. So if we're used to looking at those modern day relays that we use in the panel, the orange and green ones, double pole, double throws, or if you have a flex panel and you have a newer one from 2017 on, where we have the relay or flex panel PCB in it, every one of those has an LED in them. So when we energize that relay, the LED lights up. Again, if it's the cartridge type relay with the green base, it's an amber or yellow LED. If it's that flex panel PCB that I keep talking about, it's a blue LED. The only reason I spec a blue LED on that product is because the blues out in the field is kind of an unnatural light, and it's easier to tell if it's truly on or not. So I'm not going to really read this, but I'm going to kind of talk a little bit about it. One of the things that we ran into years ago, back into around the late 1980s, we started seeing a lot of automobiles start embracing computer systems, and instead of old-fashioned 1950s and 60s technology, we started seeing, modern day technology, what it's become, being put into automobiles. And I can remember around 1988, first thing they told us is throw away your test lights, because every auto mechanic shop had a test light, right? And they said that a test light with an incandescent bulb on it, if you tried to use it in some of these computer circuits, could put an unnecessary or overvolted load on that circuit, and it could actually damage the computer or the ECM or what was producing that voltage. And so they told us, throw all your test lights away. And they came back and said, if you have to have a test light, you can actually build one. Nowadays, you can go out and buy one. But the concept was, you use a LED, but the LED by itself, connected directly to voltage, will blow real quick. So you always have to insert a resistor in it. So we talked about resistors a few weeks ago. In this case, on a 9-volt system to a 12-volt system, a 470 ohm resistor with a modern day, just a cheap LED works real good. You use that and you got a great LED. Personally, I like to just go to the store nowadays and buy an LED. Here's some exercises that we can throw through, but what I want to do is I want to revert back and show the video real quick, 2 videos actually, because we have plenty of time today, about why I think it's important that you carry today an LED test light along with a digital voltometer. And I do recommend an LED test light, but I'd like to show these videos. So I'm going to stop sharing this screen and see if I can't pull up a video or 2 real quick. We've showed them at the beginning of this session. I'm going to show them again for those of you who may have missed that session. And it's taking me a little bit longer. Okay, if you will, just excuse me for a minute, and I'll be right back, and we'll get this video going.
Everyone will just give us a moment here while John retrieves this file. We'll get back on again.
David Bell, are you still listening?
I am. I'm here.
Okay, for some reason it's not letting me in, but if you go up to where the app section is, you can see 3 different icons. One is upload and share videos.
Yep.
Will it let you access? It's for some reason it's telling me that I'm not logged in, even though I am.
Sure. Which one would you like to show, John?
There are 2 videos on voltage potential.
Yep.
And those talk about diodes quite a bit. I'm not sure
which one would you like first.
Tell me the titles of them, man.
One's a demo as an AVI, it looks like, and then the second looks like it's documents.
Yeah, let's do the document first.
Okay.
And then let's go straight into the one with the demo, because that's a kind of a hands-on demo. Hey guys, this is John Nance with Alltronic. A lot of people have been asking what is the difference between true voltage with amperage power behind it and what we call voltage potential. This day and time with a lot of solid-state electronics, it really can whoop a lot of people when they're out in the field trying to troubleshoot. So I'm going to do a best example to show you what voltage potential is, and then I'm going to make a second video that shows you kind of different ways of checking for voltage potential versus true voltage. So what I've got here is a classic excerpt from one of our panel designs where we have 103 switched fused battery power, so there's 24 volts on it, and we're bringing it into a relay, and this is just our symbol for a relay in most schematics. And this voltage, 24 volts DC, is present at all times. It also enters into a flyback diode for a remote relay to be added on this circuit if somebody wanted that option. And in this case, they would use it to shut power off to an engine control system. On this relay PR2, they're using this wire DE5 from the A2 terminal to turn the relay on and off with a digital output 5 from a DE4000 terminal module. Now, what this does is when this digital output 5 turns on, it closes internal contacts and connects it to ground, and we can have a lot of different control strategies that would do this, but then it would complete a ground path for the PR2 relay, and the PR2 relay would energize and turn on. Now I'm going to show you a different example of this section of the schematic in another schematic, and let's use it to show exactly what voltage potential is. This is from a slightly different design, from a 3000 design. The relay was renamed PR1 for it, but the same principle applies. We have wire 103 that comes through a check valve diode, so that means voltage can only move in this direction, and it enters in and it comes into the coil of the relay. Now that coil has a lot of resistance to it. It also enters into a light emitting diode through a 3.92K ohm resistor and makes it back to the DE5 wire. And then finally, there's a flyback diode only allowing excess voltage from an inductive load that occurs, or self-inductance, when the magnetic field in this coil for the relay collapses, to where if there's a voltage surge on the ground line, it can be dissipated back into the system and loop around in this path and slowly diffuse. So if DE5, now this DE5 wire comes from the A2 terminal, again, it's tied to all these things you see here, and it goes back into digital output 5 on either the DE3000 board or the DE4000 board, as I showed in that previous example. Now, all of this up here has to do with what the switch contacts of the relay are doing. So this is irrelevant. Don't even think about this for right now. But remember, voltage is just like pressure. So if I measure voltage between a ground point in the panel and any of these points along here in the schematic, I'm going to have 24 volts. But if I don't have this circuit grounded and I measure this DE5 connection back at the digital output 5 and I hadn't switched on the ground, I'm likely to see 24 volts with a digital volt ohm meter. And that is because with a not a completed circuit, the resistance factor of it's taking place in here and right here is irrelevant until I complete the path of the circuit. So as soon as I ground this circuit, the voltage will dissipate and drop to 0, or should, provided my ground path is sufficient enough to handle the voltage that remains after the resistance. That's a short, quick example of voltage potential. Again, with the ground path not completed, I'll see voltage, the same voltage here as I do here. With the ground path completed, the voltage on this side, because the resistance will drop. Think of it as a water hose. If I plug one end of the water hose, but then pressure it up, but then shut the supply pressure up, there's still pressure on that hose. But as soon as I opened the discharge into that hose, the pressure escapes out immediately, and then there's no more pressure. So think of the voltage in that manner. Thank you for your time. If you have any questions, please email me at jon.nance, N-A-N-C-E, at herbiger.com, H-O-E-R-B-I-G-E-R. And look for the next video because I'm going to show an example of how to test for true voltage versus voltage potential. Thank you and have a great day.